Okay, well, next we'll differentiate some hyperbolic functions. So remember that the definition of the hyperbolic cosine, cosh of x, is just e to the x plus e to the minus x over 2, and the hyperbolic sine, or sine of x, is e to the x minus e to the minus x over 2. It turns out that cosh and sine have some rather similar properties to cos and sine, even though the definition looks completely different. And one thing that you can see rather easily is that when we differentiate cosh of x, we're going to get sine of x. So hopefully in the exercise that you did, you saw that when we differentiate e to the minus x, we get minus e to the minus x. And that means that when we differentiate cosh, we differentiate e to the x, we get e to the x again. We differentiate e to the minus x, we get minus e to the minus x. And so when we differentiate cosh, we get e to the x minus e to the minus x over 2, which is exactly sine. And in exactly the same way, when we differentiate sine, we get e to the x minus e to the minus x, or e to the x plus e to the minus x over 2, which is exactly cosh. Once again, if we define the hyperbolic tangent as sine over cosh, we can use the quotient rule to work out what the derivative of the hyperbolic tangent is. You can use this as an exercise if you want. If we differentiate the hyperbolic tangent, tan h, or tan of x, we get 1 over cosh squared, exactly as we did with tan. The derivative of tan is 1 over cos squared. When we differentiate tan, we get 1 over cosh squared. And that is sec squared, the hyperbolic secant. There are many functions that don't have inverses. And here's one example. Here's y equals x squared. Let's try and think about what f inverse of 4 should be. So we're trying to find the values of x where x squared is 4. So here's 4, say. And we want the values of x such that f of x equals 4. Well, here's one value, of course, 2. But there's also another value, minus 2, over here. And of course, the property that we wrote down of the inverse function means that we would have to have f inverse of 4 must be 2, and also f inverse of 4 has to be minus 2. But f inverse is meant to be a function, which means if it has one input, it should only have one output. So we can't have a function having 2 values. So our problem, of course, is that the curve intersects the line y equals 4 at 2 points. We can get around it if we're a little bit careful about the domains. So we're going to rub off this half of the function. And instead, we're only going to think about the function y equals x squared when x is greater than or equal to 0. Well, this then does have an inverse. If I give you any value of y, or there's any value of y which is non-negative, there is then a unique value of x that gives that value of y. And that means that we can define the inverse function. So the inverse of y equals x squared for x non-negative is of course given by the square root. And again, we're choosing the positive square root here. Well, now we can differentiate x squared and the square root of x. We've done both of those already, and what we're going to do in the inverse function rule is to see how they're related. And we're going to be able to check our rule in this particular example. So let's work out what the rule is now. In fact, it's actually very easy to work out the derivative of the inverse function. So let's now write g for f inverse. So write g for f inverse. So we're supposing that f is some function which does have an inverse. Then g has the property, remember, that y equals f of x exactly when, so we write exactly when x is f inverse of y, or g of y. So in particular, g of f of x, well, what is g of f of x? Well, g is the inverse of f. If y equals f of x, then g of y is x again. So g of f of x is x. And we're going to apply the chain rule on this equation. So the chain rule gives the following. So when we differentiate the left-hand side, we get f dash of x times g dash at f of x equals, and when we differentiate the right-hand side, well, we know how to differentiate x, it's just 1. This is just x to the power 1, so it becomes 1x to the 0. Now, if y equals f of x, then we can see that we get g dash of y equals 1 over f dash of x. And this is the inverse function rule. One last thing about this rule here. So remember that if y is f of x, then we could write f dash would be called dy by dx. And similarly, if x is gy, then g dash is going to be dx by dy. So sometimes we could just write this rule in the alternative form, dx over dy is 1 over dy over dx. And that's another way we can write the inverse function rule. Let's do one example of the inverse function rule. And we've already seen the example. We'll do y equals x squared. So f of x equals x squared. And remember, this is only going to be for x non-negative. And then in that region, it does have an inverse. The inverse is g of y is the square root of y. Well, let's work out g dash using the inverse function rule and check that it agrees with what we found earlier. So, g dash of y. Well, first we work out f dash of x. And f dash of x we know is x to the power 2. It becomes 2 times x to the power 2 minus 1, 2 times x. And then our rule tells us that g dash of y is 1 over f dash of x. So 1 over 2x. Well, really, we should be putting these in terms of y. So we don't like having g dash of y in terms of x. We'd like g dash of y to be given in terms of y. But of course, x is gy, so x is just the square root of y. So this is 1 over 2 root y. And that agrees with what we saw in the first video.